Hey you guys, it's Miss Arneson, and I'm going to tie together some things about chemical reactions versus nuclear reactions, the difference between them, and the results of nuclear reactions, which are going to be the radioactivity and the ionizing radiation that we talked about being in Chernobyl. Before we can really look into a chemical reaction, I need you to review what a chemical is. So the periodic table of elements is an arrangement of the chemical building blocks of matter. So we have everything from hydrogen down to this one, which kind of has a name. We don't really know very much about these last little ones right here because we can only create them in a lab for like a second, but a lot of these other ones exist in nature. And we're going to be talking about these elements and we need to be able to refer to them and know the number of subatomic particles they have. So let's look at this information that's right here in a periodic table square, just so that we can use that for our understanding. So this is going to be the atomic symbol, the atomic name. Those are two things that we really need to pay attention to. This one has a lot more information that we don't really need to care about in this class, but I just put it on here because I don't want it to freak you out when you see a periodic table block that has more information on it than you need. I just want you to find what you need. The other information you'll need besides the name and the chemical symbol is the atomic number. The atomic number is the most important number associated with any element. Krypton's is 36, hydrogen's is 1, helium's is 2, and you can find those are usually going to be the bigger number. By bigger, I mean like the size bigger number, the bold one on here. The bigger number is going to be something called the atomic mass. I know it says weight on here, but we are going to call it the atomic mass. So I just wanted you to know that that's what you can find that we need to care about in this class, although there's plenty more. It's a really amazing table. Okay, so right here we're going to be looking at the way to find out how many subatomic components or subatomic particles, that being the protons, neutrons, and electrons, are in an atom. And we're going to use krypton as an example. So the atomic number of krypton is 36, and you definitely need to write down that the atomic number tells you the number of protons in the atom. And the number of protons defines an element. So if you have 8, it's oxygen. If you have 36, it's krypton. So those numbers will never change. The number of electrons and neutrons in an atom can change though. So we need to be able to figure out how many we're dealing with when we are doing chemical reactions or looking at nuclear reactions. Okay, so in this case, the atomic mass of krypton is 83.80, and I put 80 because it's a little bit more accurate. This one has 83.8, but it doesn't really matter for us because we don't have to worry about significant figures yet. When we round the atomic mass, we're going to get something called the mass number. And the mass number is really important for us to figure out the number of neutrons in the atom. So we need that mass number. So what is 83.80 rounded? Well, we're going to take this number right here, and if it's higher than 5, we're going to keep this number, or we're going to take this number 1 higher, and if it's lower, then we just keep it the same. So since it's 8, which is higher than 5, we're actually going to have our atomic mass, in this case, rounded to our mass number, 84. So the mass number for krypton is 84. And 84, the mass number, tells us the number of protons plus the number of neutrons. And I know it's a decimal point, but that's because it's an average of all the kryptons we've ever measured. And we can't deal with part of a neutron, so that's why we have to round it. You can very easily do this in your head. Some of you, you'll be like, oh, well, if I know the number of neutrons, number of protons, and this is protons and neutrons together, then I just need to subtract. But I like to look at it as an algebra problem. So we have our result is 84. That's our mass number. That's the number of protons and neutrons together. So if we put protons right here as 36, and we're just going to call what we're solving for x, which is the number of neutrons. You could even put n with a little 0 right there to represent neutrons instead of the x if you wanted to use that as your variable. Well, then you would say 36 minus, we need to get rid of that 36, minus 36 on the other side. And what you would get is x equals 48. So the neutrons in the most common isotope of krypton is 48. So that's really important to be able to find. Now, there's going to be different types of elements that you can find out about. Like, for example, there's uranium-235, there's also uranium-236. And those numbers we'll look at a little later, but basically you're just going to take whatever that number is, like uranium-235, and then you would subtract the atomic number, which in the case of uranium, I believe, is 92. Okay, for finding electrons, we're going to usually assume that it's the same as the number of protons. So we're going to assume that it's the same, except for ions. We talked about ions at the very beginning of this unit because ionizing radiation is bad because it charges your particles in your body, and then they want to have chemical reactions, and that's not good for cells that are not supposed to be doing that. So this is how we would write an ion. In some ions, it could be like chlorine plus 2, depending on what ion you're talking about. Okay, chemical reactions are when one group of chemicals turns into another group of chemicals. So we have this arrangement of carbon, hydrogen, and oxygen atoms. Right now we have methane and oxygen gas. In the middle where this arrow is, that's where the chemical reaction is going to happen, and afterwards we still have carbon, oxygen, and hydrogen. But now they're in a different order. It's like we had these Legos represented by each of these little spheres. We took them apart and we put them back together in a different arrangement. But we have the same number of black atoms representing carbon before and after, the same number of red ones representing oxygen before and after, and the same number of the hydrogens, which are represented by the white spheres. So this is a chemical reaction. Matter is going to get transformed. Sometimes these absorb energy, sometimes they will give off energy. The electrons are going to be changing position, and an example is burning. So this is combustion of methane right here in this picture of this chemical reaction, which is drawn here for you representing atoms. This would be the chemical equation or the formula that you would use to solve for this. And then this is just fire because fire is cool looking. Okay, nuclear reactions are different. They're going to turn some matter into energy. So we will not have the same number of chemicals at the beginning and the end anymore. We're not going to have these are deuterium and tritium are both types of hydrogen. Since they have only one protein, they're just different isotopes. And afterwards, we do not have any more hydrogen. We have helium. So we're literally changing the chemicals here into other elements. Some elements are getting changed into other elements. That's very different than here, where you have the same elements on both sides, but they're just put together in a different order. Here you have clearly different elements. That is the major difference. And we're always going to release energy in these reactions. So we're always going to have a ton of energy output here. And this is an example kind of what fusion looks like in the sun. You take two hydrogens, you smack them together really hard, you get a helium, and this extra neutron goes off and forms some radiation in the form of neutron radiation, which is a type of particle radiation, and you get a bunch of energy. Yay! That means we can live on the Earth because the sun makes so much energy. Okay, so this is something that I hear a lot of times, that fusion and fission create a lot of energy. And if you remember the first law of thermodynamics, it says matter and energy can't be created or destroyed. You cannot have more of the energy at the end than you had at the beginning. You can't have more atoms in your products than you have in your reactants. And that seems so weird when you're talking about something like an atomic bomb. So here's an atomic bomb. It's really small, and this is a picture of Nagasaki in Japan before and after it was bombed. You can see there's all kinds of buildings and structures and parks and plants and all kinds of lovely things here. And after this bomb went off, it destroyed everything. When you think of a chemical reaction bomb, so like you've seen an explosion of a car in a movie, and it's a really big explosion. Let's say multiple cars blow up. It just basically blows up really close to the car, the really close surroundings. When it comes to this type of bomb, when we're actually changing the elements themselves into other elements, we are getting a lot more energy released. The scale of energy is just astounding. It's almost, it's unbelievable almost. And so when we do that, we are doing something completely different than a chemical reaction. But we are not creating energy. What we're doing is we're taking the teeniest, tiniest little amount of energy that you can't even imagine, and we're changing, of matter. So we're taking a little teeny bit of matter and we're changing that into energy. If you remember Einstein's famous equation E equals mc squared, that's basically what it means. If you take a little bit of matter times the speed of light squared, you can get how much energy it would turn into. And that is a lot of energy. But just to show you, we are not really like getting rid of anything here. We're just changing its form a little bit. So if we take uranium-235, 235 would be the number of protons and neutrons, and we add an extra neutron to it. We whack this neutron into it really hard. What happens is it stays there for a second, well, not even a whole second, but it gets really unstable, and so the uranium splits apart into two smaller elements called krypton and barium, and it releases a ton of energy and also some neutron particles. So with this, if we added all of these up, which I'm going to do this math really quick for you, some of you will be able to follow it and some of you will glaze over. So if we have 236, that's really where we're starting, right? Because we had this 1 plus 235. We have 236 minus 92, which is the atomic number of uranium, gives us 144. So here, before our reaction, we have 144 neutrons. After our reaction, we have to say 92 minus 36, which equals 56, plus 141 minus 56, which equals 85. That would equal 141. So where are those 3 extra neutrons? Well, those are being released by themselves. They're not going to be part of either of these nuclei. And so that altogether gives us 144, just like we had when we started off. The same thing you can do with the protons. If you look at the number of protons, 56 plus 36 will equal 92. Oops. Okay, 92. So we are not destroying any matter. We're not destroying any energy. This energy is coming from a teeny bit of matter that we can't even really count in a high school level. We don't really need to get that sciencey. That is the tiny amount that's turning into all this energy that can basically take apart a whole city. So here's another example, because I feel like 2 examples are good for something that's difficult, but this one is not that one. So this one right here, we took something bigger and we broke it down into 2 smaller pieces, which you guys remember is called fission. And here we're taking 2 smaller ones and we're putting it together into a bigger one, which is called fusion. So hydrogen 2 means that it has 2 particles in the nucleus. One is a proton, one is a neutron. 3 means hydrogen 3, 1 proton, 2 neutrons. And we whack those together and we get a helium, which has 2 atomic particles that are protons, which define it as helium. And then this extra neutron gets released. Now there's different kinds of radiation that can be released from all of these. So you can have neutron radiation, but you also get light energy. And so there's other types, gamma radiation. And I just want you guys to know that all kinds of radiation can come from these reactions. There's one more type of nuclear reaction that is super weird, and you don't have to talk about it very much until you get to college if you start doing these things in college, but it's called radioactive decay. And basically, this is like so weird, and we can't fully explain it. It's something that happens because of a weak nuclear force that's inside of all of the nuclei of all atoms. And basically what happens is that one of the parent isotopes, so element at the beginning is the parent, one of those protons just changes into a neutron. It's like, hey, I'm just changing into a neutron for really no good reason, just because we can measure it. It happens every certain number of years, but why is still kind of a mystery. When this happens, you can get 3 different types of results. The results will all give off a different type of radiation, alpha, beta, or gamma. And so this is the type of radiation that has been studied studied first, really by people who were the early chemists, and they figured out that this was happening. And then, of course, with more time, we figured out that we can actually control nuclear reactions, and we started doing fission and fusion to generate power and make bombs. Although we made bombs before we used it to generate power. Sad, but true. Okay, the last thing I want to talk to you about, and this is going to tie in to our class really well, is that when you have these different reactions, they're getting off different types of energy. And we can either think of these as rays or particles, because they're kind of, sometimes they're the same. So X-rays and gamma rays are going to be carried by photon particles, and then the rest of these have other types of particles. Neutron's easy to remember because it's a neutron particle. And they can go through different materials. So basically, the materials that it can go through kind of shows you how damaging it is. So in this case, we're going to say neutrons would be definitely the most dangerous type of radiation because it can go through the most different materials. It has a really high amount of energy. If we were looking just at the types of radiation that are on the electromagnetic spectrum, then we'd be talking about the X-rays and the gamma rays. And these can go through a lot of different types of material too, but they can't go through lead. So if you recall on Chernobyl, they had egg baskets, which they were using to cover their manhood. And that's because they didn't want to become infertile. They didn't want anything to happen to their testicles. And so they were covering those. I think it's interesting that they were more interested in covering their testicles than their brains, because if I had to choose between that, I would choose my brain. But, whatever. Covering your whole head is harder, I guess. You'd need a lot more lead. So these different materials are used in different ways. So that's why when they're burying the people, they bury them in these big concrete structures, because the concrete can actually stop the types of radiation that are ionizing and can come out and damage your skin cells or your DNA or anything like that. I really hope that you guys can connect this science back to the class, and a lot of the things that you're learning in this lesson are going to be on your final exam, so make sure you don't blow it off and ask me questions. Email me questions, text me questions if you have any, and I will get back to you. Have a great day.